Okay, this is FRQ set 6. We're going to start with number 1 here. Number 1 says, let f be a function with f of 4 equals 1 such that all the points x, y on the graph of f satisfies a differential equation dy over dx equals 2y over 3 minus x. So as you can see, there's two different functions here. There's f of x and g of x, two different conditions, slightly different in the difference in the variables here. So first one is very straightforward. It says part A, find y equals f of x. That means you're solving for the equation given the initial condition of f of 4 equals 1. So separate your variables and solve for them separately, take the integral separately. So I'm going to save myself some room up here and do my work down here with you. Let's see. All right, so what I'm going to do is I'm going to separate my variables, keep my dy on the left, and move the 2y over to the other side too. So dy over 2y equals 3 minus x dx. Take the integral of both. Keep in mind then on the left-hand side, this is 1/2. Natural log of y equals 3x minus x squared over 2 plus c. At this point, I plug in the initial condition because I don't want to solve for y yet. That way it will interfere with my c, the value of c if I solve for y right away, right? So let's plug in 4 for x, 1 for y. So you have 1/2 natural log of 1 equals 3 times 4 minus 4 squared over 2 plus c. So natural log of 1 is 0. That's awesome. So 0 equals 12 minus 4 squared is 16. 16 over 2 is 8 plus c. So 0 equals 4 plus c. c equals negative 4. Right? So then you go back to your original equation. You have 1/2 natural log of 4 equals 3x minus x squared over 2 minus 4. Multiply both sides by 2 to get rid of 1/2. Natural log of, not 4, sorry. Natural log of y equals 6x minus x squared minus 8. And then lastly, take e to the both side. So your function y equals e to the negative x squared plus 6x minus 8. I typically like to rewrite it in standard form so I don't lose any of my terms. Okay? All right, nice and easy. Part B, it says that given that g of 4 equals 1, find a limit as x approaches infinity of g of x and a limit of as x approaches infinity of g prime of x. Note it says it is not necessary to solve for g of x or to show how you arrived at your answer. So that's a clue to you that there's a shortcut in this. You don't actually have to do separation of variables. You can notice that there is the y and 3 minus y. So the key here then is to see that because there's two y's there, this is a logistical regression equation, right? The logistical regression, if you actually solve for this, it's just a lot of work. So if you recall, logistical regression has this has a formula dy over dx or dy over whatever your independent variable should be. But this is your k. Typically, this is k p times m minus p. K is the rate at which this regression is happening. M is your carrying capacity. So because it's a logistical equation, you can see then that m, your carrying capacity is 3. Then that means that's a limit as x approaches infinity of g of x, and it will equal to 3 because the graph looks something like so, right? This is a logistical regression equation, which means then the derivative of that is going to be horizontal as it approaches infinity. It's a horizontal asymptote. So from the graph, from the fact that we have the knowledge of logistical regression, we know then the carrying capacity is my limit for g of x, and then because it's a horizontal asymptote, the limit as x approaches infinity of g prime of x is 0 because the slope of that is 0 up top. Okay? All right, and then lastly, it says part C, for what values of y does the graph of x have a point of inflection? Find the slope of the graph of g at that point of inflection. It's not necessary to solve for g of x. Again, a logistical regression equation looks like this, where you can see it's concaving up, pause, and then concaving down. Again, it may not cross through the origin. So it usually looks something like this, right? Where this is your point of inflection. So the point of inflection actually happens when you are halfway at the halfway of your carrying capacity. So carrying capacity is 3. Halfway of carrying capacity is 3 over 2. So when y equals 3 over 2. So then what are you going to do? You're going to use that. It says what is the slope at that point of inflection. So you can plug in that y into this into this function right here, right? So dy over dx equals 2 times 3 over 2. 3 minus y, which is 3 over 2 again. So you get 3 times 3 over 2. My final answer of the slope will be 9 over 2. Okay. We're on set 6, number 2 now, right? So it says, at the beginning of 2010, the landfill contains 1,400 tons of solid waste. The increasing function W models the total amount of solid waste stored at the landfill. Planners estimate that W will satisfy the differential equation, this right here, for the next 20 years. W is measured in tons, T is measured in years from the start of 2010. Okay. A says, use the tangent line tangent to the graph of W at T equals 0 to approximate the amount of solid waste that the landfill contains at the end of the first 3 months of 2010, where T equals 1/4, right? So part A says at 2010, so we're going to use the tangent line. It's a linear approximation, right? So you need to find your tangent line first. So part A says at 2010, you have, that is your start. So your T equals 0 at that point. Your starting point is T equals 0 and your waste is 14,000. So W equals 1,400, not 14,000. That's too terrible. Okay. So what is your slope at this point? Because to write my logistical regression, not only do I, to write my tangent line, I have my point, T equals 0, W equals 1,400. I also need my slope. So you need to plug this into your slope function here to figure out what the slope is for our linearization. Okay, so dW dt equals 1 over 25. W, so 1,400 minus 300. So that gives me 1 over 25 times 1,100. That would be 44. Okay, so your linear approximation is going to be L of x equals 44 is your slope. X minus 0, so times T, or T minus 0 is T, right? And then plus 1,400. And then it says to estimate T equals 1/4. So you're going to use this one more time to do my approximation. That's the whole point of this. So L of 1/4 equals 44 times 1/4 plus 1,400. That's 11 plus 1,400. So 1,411 tons will be your approximation. Okay, tons. Okay. Moving on, it says find the second derivative of W. It used the second derivative to determine whether your answer is an underestimate or an overestimate of the amount of solid waste at that point. So you're looking basically at concavity. Keeping in mind that if it concaves up, your tangent line is going to be underestimate. If it concaves down, your tangent line is going to be overestimate. So you're trying to figure out the concavity, whether you have a positive second derivative or a negative second derivative. So let's take the second derivative of my first derivative. Your second derivative here is d squared W over dt squared, coefficient 1 over 25, W minus 300, so then that would be W prime, and then minus 300 is gone, right? So don't forget, then you need plugging your W prime back into this equation because you don't want to have a prime in your answer for the prime. So that would be 1 over 25 times another 1 over 25, 1 over 625. W minus 300 is my second derivative, right? So then it says at the point of T equals 1/4, this is going to, where am I? Yes. So at the point that we were estimating T equals 0, W equals 1,400, you plug that in, you get 625, 1,400 minus 300. You don't need to care about the actual answer. You know that the fact that the answer is going to be greater than 0. So this concaves up. So because it concaves up, my linearization in part A is going to be an underestimate, right? So therefore, this is going to be an underestimate. Okay, all right. Moving on, part C. Find the particular solution, W equals WT, to the differential equation with the initial condition. So you're just going to solve for this. You're going to separate your variables and solve for your original equation. So you have dW over W minus 300 equals 1 over 25 dt. Take the integral, so natural log of W minus 300 equals 1 over 25 T plus C. Again, my habit of plugging my initial condition at this point, W equals 1,400, T equals 0. So natural log of 1,400 minus 300 is going to be 1,100 equals 0 plus C, so C is 1,100. So you have natural log of W minus 300. And notice again, I didn't put absolute value around my W because this is the amount of solid waste. You're never going to get negative amount of solid waste, so you don't need the absolute value around it. It's not going to give you a negative value here, right? So then you have T over 25 plus natural log of 1,100, right? And then E of both sides, so W minus 300 equals E to this whole thing. Keep in mind that what that will do is it's going to bring down 1,100 as my base. So you have W minus 300 equals 1,100 E to the T over 25. And last but not least, add the 300 over, so you'll get your final answer. Okay?